A very important notion in the theory of differential equations is that of stability, right? So if we have an autonomous system of ordinary differential equations with n unknown functions, and we have its critical points, then such a critical point is called stable. Well, you can read the definition, right? So for every epsilon, there exists delta, and so on, blah blah blah. Well, a little challenge for you. In this illustration, is epsilon the radius of the small circle and delta the radius of the big circle, or is the other way around? So I suggest that you pause the lecture and you try to answer this question, and then you continue watching, and you compare your answer with mine. Okay, so let me explain. Now, notice that the main point about it is that the trajectory that begins inside the small circle will never leave the big circle. All right, so if a trajectory begins inside the small circle, so it will never leave the big circle. So the radius of the big circle is, well, let me try to make it clearer. So the radius of the big circle is epsilon. So meaning that this condition, that x of t minus x naught is less than epsilon. All right, so this condition tells us that the trajectory will never leave the big circle. All right, so this condition that the trajectory will never leave the big circle is this. Well, at the same time, the radius of the small circle is delta. So which means that every solution satisfying this condition, so x of 0 minus x naught is less than delta. All right, so it means that the distance between x of 0 and the critical point is less than delta. So in other words, it means that it begins inside the small circle. So it's not going to leave the big circle. So this is what it really means, that for every circle around the critical point, there exists a possibly smaller circle, such that every trajectory that begins within the small circle will never leave the big circle. Okay, so that was just stable, without the word asymptotically. So, but then a critical point is called asymptotically stable if it is stable and all trajectories that begin within some distance from the critical point, they are going to eventually converge towards the critical point. So this is stability. So a little challenge for you, well, that will help. That will also help you to understand the notion of uniform convergence is, well, try to rephrase this using the notion of uniform convergence that you learned in real analysis. Okay, and then a tricky problem here is that explain why this condition alone is not sufficient for stability. So in other words, it is possible that a critical point of a system of autonomous differential equations is such that all trajectories in a certain neighborhood, they're going to eventually approach the critical point, and yet the critical point is somehow not stable. So it's not even just stable, not speaking of asymptotically stable. So in other words, this problem explains why we have to specifically require that in the definition of asymptotically stability, that the critical point has to be stable and something else. Okay, and here is a little quiz for you.